So this is, remember, this is in meters, and if you put all these value, and then we'll get this thing into 10 to the power minus 10 meters, right? So let's say if I want to calculate the first orbit, right? Radius of the first orbit. So that would be how much? So that would be how much? So let's say, oh, so that would be 0.529. N is 1 square, right? And let's say we are calculating for hydrogen atom, right? So this would be 1. This is, so this would be angstrom, means that this would be 0.529 into 10 to the power minus 10 meters. So this would be the first orbit, radius of the first orbit of the hydrogen atom, right? We are talking about the hydrogen atom. Similarly, we calculated the velocity, right? Velocity of the electron, and this came out to be this thing. But we call this constant as Sommerfield's constant. And when we go, when we guys will go to the higher classes, then you guys will understand the importance of this thing, right? So if you guys want to get a Nobel Prize, then you guys we can figure out that how this value comes up, right? From where this alpha comes up. So if you guys can figure it out, then you guys will get a Nobel Prize, right? So this is an open question. But this constant is called Sommerfield's constant, and its value is 1 by 157. So this is the velocity of the nth orbit we got, right? And this is going inversely over n and directly proportional to the atomic number, right? So if you have a higher atomic number, then this velocity would be larger. So this thing we understood. And then lastly, we reached up to this point, time period. So how much time it is taking to cover one revolution, right? So this was the time period, and similarly, we can calculate the frequency as well. So frequency would be how much? 1 over time period. So that would be z square m 4 divided by 4. This is n cube, and epsilon naught square h cube, right? So I'm sorry that if you guys got confused in my notation of n and h, then I'm sorry, right? If you guys have any confusion about my handwriting about n and h, then please tell me, right? Okay, so these are the things that we got in the class. Now, let's calculate the total energy of that revolving electron. Right, let us calculate that. So this part, yes. Now let us calculate the third part or the fourth part is total energy of the, right. So what is the total energy of the orbit? So as we all know that total energy would be kinetic energy because the electron is moving, and then potential energy because we have this electrostatic potential, right? So there would be two kinds of energy: kinetic energy due to motion, then potential energy due to the charge of the particles. So we have this nucleus, right? We have this nucleus which has Ze proton, and this electron is revolving around that. Yes, this radius, as we have talked about earlier, this is nth. This velocity is Vn, right? So we can write the property that we use. Then what is providing that centripetal force? So that we already know that centripetal force is provided by the Coulomb force, right? That we already know. Centripetal force is how much? Arsalan, sir,
Yes.
what is centripetal force? Yes, this is moving in a circle. So what is the centripetal force? Arsalan, that we have already done in the nth orbit, radius orbit calculation.
Yes, sir.
Yeah, so yes, sir, but what is the answer, sir? Okay, yes, Mariam, yeah, you are correct. So what is the centripetal force? That is 11th standard, right? Or
Yes,
maybe,
sir. Centripetal forces mv square by
yeah, absolutely correct. Then why were you hesitating, right?
yes, sir.
Be confident, right? Whatever right or wrong answer, be confident, right? That is why, or that is how you can overcome your vibe. So in my vibe, in my graduation and 12th standard days, whatever the examiner asked, so I didn't know what I was replying. So I was so confident about my answer. Yeah, so don't hesitate. Whatever answer is coming into your mind, so just reply. Okay, so Coulomb force, that would be how much? That would be K Q1, which is this is the electron which is revolving, right? So this E, and then this nucleus which is ZE
ZE
divided,
square
yeah,
by Rn.
square, right? So K Q1 Q2 by R square. Yeah, absolutely right. So this Rn cancel. And yeah, why I'm calculating this thing again? Because this we will need. So let us calculate this K Z square by M R. This is the velocity square that okay, what is क्या हुआ? Okay, so yeah, so this is the velocity that we get. And why am I calculating this thing, you guys? So you understand. So we have to calculate the kinetic energy first. What is the kinetic energy of the electron? What would be that? Okay. Kinetic energy due to motion. Yeah. So half mv square, right?
Half
Half,
mv n square.
yeah. So half mass of the electron which is moving and then Vn square. So that is why we were calculating this Vn, right? So this Vn square we can put back.
Yes, sir.
So half m and v square is kz e square by m r. So we can cancel, and this would be how much? K Z E square by 2R.
Sir,
Yes,
sir, wouldn't it be the whole raised to 2?
the whole square.
Yeah, the whole square.
So you
Because
see,
it's
yeah, you see that we have directly calculated Vn square. We have calculated this Vn square. We didn't calculate this Vn, right? So Vn
mm,
square, we directly calculated this Vn square. And this Vn square value we are just putting it, right? Is it okay?
yes, sir.
Yeah. We just directly wrote this V in square value, right? So kinetic energy, how much? Yeah. Okay, so Rn, this is the kinetic energy that we have, right? And then let us calculate. Should I name these things? Yeah, let us name these. Let's say this is one. Let's say this is two. And now we have to calculate the potential energy, right? So remember your first chapter. What is the potential energy, guys? We have what is the potential energy of two charge particle with separation Rn? What is the potential energy? K Q1 Q2 by, right? This is the potential energy. So we have one charge particle is nucleus, Ze. One charge particle is electron, so minus. Then how much we'll get? So that would be K, right? And Ze minus E divided by R. So how much is this? Let me write Z as this, right? So it will be confusing. This is looking like, so let me write this Z as, right? Right, guys? So this would be how much? This would be K, Z, and minus E square by. So this is my potential energy. Now, let's call it 3. So now let us calculate the total energy. Total energy, that is kinetic energy plus potential. So kinetic energy is how much? That is kZe square. Kze square by 2Rn. And then potential energy is minus Kze square by Rn. Right. So then what would be the total energy? That would be Kze square by 2Rn minus Kze square
Sir,
by
1 by 2?
yeah. So we can take this thing common, right? So Kze square by Rn is common, so this is half minus 1, right? So we are subtracting half from minus 1, or we are adding half in minus 1. So that would be minus 1, right? This would be minus Kze square by, right? So how much is this value? Kze square by 2Rn. That is
Kinetic energy.
kinetic energy, right? Then we can write the total energy as minus of kinetic energy, or we can also write potential energy is how much? This thing, and if we divide it by 2, right? Then
Yes.
it will become the total.
Total energy.
These are the relations, right? If somebody gives you that, let's say you have an electron whose total energy is, let's say, yeah, this simple question calculate. So let's say we have this question. We can directly write it, right? So let's say that the electron in hydrogen orbit has energy, let's say minus, it should not be, let's say we are just writing minus 2 electron volt, right? Because the electron has discrete energy, right? So it can have only a specific energy, not this minus 2. So we'll calculate that and let us that and then. Okay, so we have got all the energy. Now let us put all the values, right? E is how much? This is minus K is let us Z E square by 2 and Rn. Rn we have already calculated. How much is this Rn? Back and see Rn. Rn is Yeah, Rn is h square epsilon naught n square, right? H square epsilon naught n square by z m square by. So this is minus k z e square by 2 h square n square epsilon naught by oh, what is the other thing? H square h square epsilon naught n square z m e square by z m e square z m e square by. So this is the value that we will get. So what would be the total energy? This is minus k z e square into z m e square pi divided by h square n square epsilon. So let us write the value of k as well. So this would be how much? Minus z square, right? And this is e square and m e square pi divided by 2 and h square n square epsilon naught and then this 4 pi epsilon. So what is cancelling? Only, oh, you have raised hand. Yes, Mariam, did you say?
Sir, wouldn't it be e raised to 4?
Yeah, so e square and e square, that would be, yes, you are correct. Yeah, so that we are going to write it down. So this thing would be how much? So we have minus z square, and let's say this is where is n? This is minus. This is n square, right? And all the other things. So this is m e4 divided by h square, and this is epsilon naught square, and this is 8. 8 epsilon naught square, and do we have anything else? Yeah. So this value, right? So if we put all these values, because this mass of electron is how much? That is 9.1 into 10 to the power minus 31, right? Or whatever. So this value and E is 1.6 into 10 to the power minus 19, and this H is 1 point or 6.626. Yes, 6.626 into 10 to the power minus 34 epsilon naught. You guys please check all these values, right? What are these values? So epsilon naught is 8.85 into 10 to the power minus 12. So if you put all back all these values, right? Please check these values. Maybe I can be wrong. So then you will get the value to be minus, this value is 13.6 and z square divided by n square, and this would be the energy of the nth orbit, because this is n, right? So your energy is quantized, and this would be in specific unit. So this would be in electron, right? This would be in electron. So this value, whatever this value is, it gives minus or 13.6 electron. This is the value. Is it clear, guys?
Sir,
Yes.
sir, where did the K go?
Where did K? Oh, this K.
Yes.
So this K is what? This is 1 by 4 pi epsilon, right? So that I have, this K I have put in here,
Oh,
right? Yes. This is the value that I have. Okay, so is it clear? So this would be the energy of the nth orbit, right? So if let's say I give you a question like this, that what would be the orbit or number of orbit? What would be the number of orbit of helium, let's say plus ion, so that its energy is equal to the first orbit of hydrogen, or its is equal to its energy is equal to the energy of the energy of the first orbit of hydrogen atom. Right, so this, what is this question tells? That you have this helium positive ion, right? This is a hydrogen-like atom, and this atom or its energy is equal to the energy of the first orbit of the hydrogen atom. So what is the energy of the first orbit of the hydrogen atom? That would be E. So let us calculate, right? Let's calculate what is given in this question. It is given that the nth orbit of the helium plus ion, that is equal to the first orbit of hydrogen, right? So this is given, and you have to figure out what would be n number of orbit of this helium ion. This is the question, right? So what do we know? We know that En is minus 13.6 z square by n square electron. So for hydrogen atom, we know that Z is 1, and we are calculating the first orbit. So N is 1. That is given. So this would be how much? E1 would
Minus
be,
13.6.
yeah, so this would be simply minus 13.6. Right. Now we have to calculate, yeah, this is the electron volts. Now we have to calculate for helium plus ion. So what is Z? Z is 2, right? And N we have to figure it out. So if we calculate En of helium plus ion, that would be minus 13.6. That is 2 square, right? Divided by this N
N
square.
square.
So this, and from the question it is given that En helium plus, that is equal to E1 hydrogen. So if we put all these values minus the electron, so this is 2 square divided by n square, and this is equal to minus 13.6. So this will cancel, minus minus will cancel. So n square would be 2 square. So n would be, so the second orbit of the helium atom will have the same energy as that of the first
Hydrogen.
orbit. Yeah, first orbit of what is that? So the first orbit of the hydrogen. So this was the question. And if I ask you that what would be the second question I can ask, that what is the kinetic energy and potential energy of the electron in in the first orbit of hydrogen atom, right? So we know that what do we know? We know that total energy of the hydrogen atom in nth orbit, that is minus 13.6 z square by n square. And for hydrogen, z is 1 and n is 1. So E1 for hydrogen is simply minus 13.6 electron. Right. So this is the total energy. Then what would be the kinetic energy, guys? What would be the kinetic energy?
Minus kz e square by 2 Rn.
Oh, so forget about that. We now directly know the result. Just we have to use the final result. So kinetic energy is minus of the total energy, right? We have
Oh,
to just take the negative sign of energy. So that would be the kinetic energy, right? So kinetic energy would be simply minus 13.6 electron, right? Because we know that recall E is minus K. Simply and similarly, we can calculate the potential energy. Potential
minus
energy
13.6 by 2.
by 2, that would be 2E, right? So 2 into minus 13.6. So how much is that? Minus 27.2 electron, right? Because E is U by 2. So U would be 2, right? Right, everyone, is this clear?
Yes, sir.
Okay,
Yes,
so
sir.
you guys please note it down, right? From where? Yeah, from the frequency part, please note it down, right? This is the frequency of the electron. Please note it down from there, and please, please check these values that I have put. So mass of the electron is 9.1 to 2. I guess that is 30. You guys can please check those values, right? Maybe I can check it. Nine point one into 10 to the power minus 30. That is yeah. Whenever you guys want me to scroll down, please tell.
Sir?
Yes.
Sir, what is that Vn square?
Oh, Vn square. So what did we do? We compared, because this Coulomb force is providing the centripetal force, right? Because whenever something is moving in a circular orbit, so something is pulling it towards the center. That is the centripetal force, right?
Yes, sir.
So in our case, what is providing this centripetal force? The force of attraction between this positive protons and this electron which is revolving, right?
Yes,
So
sir.
that would be the Coulomb force. So I have written this centripetal force, which is mv square by r, and that is equal to the Coulomb force, kq1 q2 by r square. So then I just calculated this Vn square value, which has some purpose. So that is why I wrote it. Right? Is it? What was your question?
Sir, I was talking about the Vn square below the first equation.
Yeah. So this Vn square. This is just the square of the velocity with which this electron is revolving. That is.
Not that, sir, like the one below 1.
Right, this one. Oh, so I just,
Yes.
yeah, so this doesn't have any meaning. So I just, when I was explaining that why did we use, why didn't we take the whole square? That was your question. So that is why I wrote this thing, right? Yeah, so you can, yeah, you can, that is not needed. So I just wrote to explain you that why didn't we square this whole thing, right? That you asked. So I just wrote this thing as VH square. So is it clear to you?
Yes, sir.
This was first equation.
Sir, can you please scroll down?
Yes, is it okay with them? Just it's marked as yes. This result is important. So we don't need to calculate this whole thing again. If we just know the energy, total energy, then we can directly calculate the potential energy and kinetic energy. Whenever you guys want to scroll down. Yes, whenever you guys have noticed, hey, we didn't join again, right? That-
Sir, can you please scroll down?
Okay, let me check all these values. Yeah, so these are
Sir, the values also we have to write?
yeah, this part is not needed, right? But yeah, you guys just know that this value gives you this, right? If you put all these values, then you get this value. So that is just for the understanding purpose, right? Yes, whenever you guys have did it now.
Yes, sir, scroll down.
Yes, whenever you guys have completed, please. Yes, done, guys.
Yes, sir.
Okay, so the next thing that we have to study is about.
Sir,
Yeah, oh, yes, what happened? Did I?
sir,
Yeah.
I'm in the last line.
Oh, sorry, sorry, sorry. Got it.
Done, sir.
Then, okay, so now let us understand. So let us understand energy of the hydrogen. So what is yeah? What is that, and what conclusion can we take from this energy level diagram, right? Okay, so what do we know? We already know that what is the energy of the nth orbit, right? So energy of the nth orbit, that is minus 13.6 z square by n square, and more importantly, the unit is electron. So this is the energy of the nth orbit. So let's say we calculate the energy of the first orbit, and remember for hydrogen atom we are calculating. So for hydrogen atom, E 1 would be minus 13.6 electron volt. What would be E2? So E2 would be minus 13.6 divided by 2 square. So that would be how much? Minus 13.6 divided by 4. How much is this thing? This thing is 13.6. So this is minus 3.4 electron volt. And then what is the third one? So that would be simply minus 13.6 by 9. I'm directly writing it. This is 3 squares. This is minus 13.6 by 9. So how much is that? 13.6 divided by 9. So this is 1.51 electron volt. Then we have this fourth orbit. So let me write it directly. That would be 4 square, which is 60. So 13.6 divided by 60. So 0.85 electron volt. Oh, and I forgot to tell you guys that why this minus sign is coming. So this is telling that electron is bounded, right? Electron is bounded by the nucleus. It is not moving freely. It is bounded by this nucleus. So this is the importance of this minus sign, right? Okay, and then if we calculate, let's say E5, so that would be minus 13.6 divided by 25. So that would be how much? 13.6 divided by 25. So this is 0.54 electron. And now let us calculate the infinite orbit. Right. What do I mean by infinite orbit? So the last orbit, right, where the energy becomes how much? So infinite square. So what is something by infinity? How much is that? So that would be zero, right? Something by
Yes.
infinity, something by very large number, that would be zero. So zero electron volt in the very last orbit, right? So after that, the electron is not bounded, and it will be outside the boundary of this atom, and it would be unbounded, and it would be free to move anywhere, right? So this would be the energy diagram. So let's say that we have this infinity, n equals to infinity. This is n equals to infinity. And then we have this, let's say E5. This is n equal to 5. This is dash dash dash. And then we have, let's say n equal to, this is 4. And then we have, let's say the gap is 8, right? N equal to 3. N equal. So this energy is 0 electron. This is how much? Minus 0.5 electron. This is 0.85 electron. This is minus 1.51 electron volt. This is minus 3.4 electron volt. And this is the first orbit, which is right. So let's say we have already learned this thing from the Bohr's model that if I want to go from this level to this level, so what is the difference? What is the difference from here to here? What is the difference? That would be minus 3.4 and minus of this thing. So what is the difference between them? This is, okay, let us get
10.2.
10.6,
No, 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 no.
30.6 minus. Yeah, that you are correct. So this is 10.2 electron, right?
Sir,
Yes.
sir, but it is minus 13.6 minus 3.4,
Yeah, so
right?
let's
So it
say,
will add.
yeah, so let's say we are calculating from this higher energy level to this lower energy level. So what is the difference between them, right? Difference, not the addition. Difference we are calculating, right? So difference between these, that would be minus 3.4 electron volt. E2 minus E1, right? Minus of minus 13 point, right? So this would be the difference. Is it clear? Yeah, you can also write minus in here. So that would be that you are taking this one as the higher one and this one as the lower one. So that would be minus 10 electrons. So you're taking the difference from this thing. So if you calculate E1 minus E2, so that would be minus 13.6 minus of minus 3 point. So that would be minus 10.2 electron, right? So that is when you're taking the difference from this to this. Is it clear? Is it
Yes, sir.
yeah? Okay, so then let's say the difference between these two is how much? So that is how much? Yeah, I should not use the calculator, but now I can cheat, right? 3.4 minus 1.5. So this is 1.89 electron, and this is how much? This is 1.51 minus 0.85. So that is 0.66 electron. And then we have 0.85 minus 0.54. So that is 0.31. Right? And so on. So you guys can see that what is happening to the difference between the energy levels? What is happening to that? Yes.
Decreasing.
Yeah, that is decreasing, right? So the difference between the energy level is decreasing when we go from lower end to the higher end, right? So that is one thing. And you can see that no electron is in this region. So let's say if I say that one electron has minus 12.5 electron volt, do we have any electron which has this energy? Do we have any electron which has this energy?
No.
No, right? So which means that the electrons are at specific energies, right? They are not in the middle. So they are in this position or they are in this position, not in the middle, right? So which means that all the energies are not possible. All the energies are not possible. Only the discrete value of energy that are possible, which means that energy is quantized in this scenario, right? So this is the first conclusion that we can make, that electrons are at specific locations, which means that the energy levels of this electron is quantized, right? This is, let us write the conclusions that we can make from energy level diagram, right? So first conclusion we can make, that electrons electrons are at a specific location. Electrons are at specific locations in the orbit, not the electron, the one electron is there, right? Electron is at a specific location in the orbits. This means that energy of the electron is quantized, right? Which we can write in the form of integral multiple. So that we can also see from this thing also. That this energy is the integral multiple of n, where n goes from 1 to infinity, right? So energy is quantized, and as you said about this difference in the energy levels, so the difference in the energy levels the difference in the energy levels is decreasing when higher energy levels, right? And now let us try to understand. Let us try to understand the energy absorption thing, right? So let's say if I give the electron, which is at here, right? If I give this electron, let's say I give this electron this much amount of energy. Let's say I give this electron, let's say, so I give this electron, let's say 9 electron volt energy, right? So will this electron take this energy? Because if I give this energy to this electron, so that would be minus 13.6 plus 9, that would be how much? That would be 6, and oh, so we have to minus that, right? That would be 9.0, so this is 6, and this is how much? Right, so minus 4.6. So you can see that this energy is not there in any of this energy levels, right? So this energy level is not there, which means that this electron is very choosy, right? It will not absorb this kind of energy. So unless and until we give this electron this much amount of energy, let's say we provide this electron this energy difference, right? So this energy difference we provide it, so then the energy would be minus 3.4 electron volt, which is the energy of this second orbit. So energy, the electron is very peculiar about the energy absorption. Only that much amount of energy it will absorb, which matches the energy difference between the two energy levels, right? So let's say the electron wants to jump from this to this orbit. Then how much it will take the energy? So then we have to provide minus 13.6 plus 1.51, so that would be how much? Okay, so 0.19. This is 0. This is yeah. So this is 12. So minus 12, which means that we have to provide 12.09 electron. So if we provide 12.09 electron volt to this electron, then only it will take that much of energy and it will go to the higher energy level, right? So the electrons in the hydrogen atom or hydrogen-like atom, they are very peculiar about the absorption as well as the emission of energy. So they will only absorb or emit that much amount of energy which is equal to the energy difference between those energy levels. Is that clear, guys? Is it clear?
Yes, sir.
Okay, so this is the third conclusion that we can make, that electron will only absorb that much amount of energy which is equivalent to the energy difference between the corresponding energy levels. Right. So this is the first one. And let's say what kind of energy we are providing, right? So we know that the energy have a specific radiation has a specific frequency, right? So this delta E, that would be h nu that we already know, right? So from this scenario as well, we can say that only those frequency of energy would be absorbed, which are equivalent to the difference between the corresponding energy levels. Right. So let's say it is going from let's say n equals to n1 to n2, right? So we have to provide what amount of energy? We have to provide E2 minus E1, which would be h nu. That much amount of energy we have to provide. Only then it will absorb that energy or that frequency, right? Otherwise, it will not. So this is the fourth conclusion, and yeah, so these are the conclusions that we can make, right? You guys can note it down, and if you guys have any question, please ask. Please note it down. Okay, and if you guys have any doubts, please tell me. Yeah, whenever you guys want me to scroll down, please tell. So remember in Rutherford model, we cannot explain these energy levels, right? But with the Bohr's model, we can explain these discontinuous or discrete energy levels. That was the benefit or advantage of the Bohr's model, right? Yeah, whenever you guys want me to scroll down, please. Oh, who got disconnected? You got it. Yes, whenever you guys want me to scroll down, please.
Yes, sir, done.
Then, yeah, then please note down this part. And this is so energy will only absorb, electron will only absorb, and you can also write atom. Uh, you can also write the emission, right? Right? And in here you can also write it, right? And you can write that the energy absorbed and emitted, they are let's say whatever amount of energy you want to give this electron to increase its energy level, the same amount of energy it will emit. So this is absorption, right, from lower to higher. And if it is going from higher to lower, so that would be emission. Both the energy would be delta E would be H nu, same, and that would be E2 minus. Both the energy are the I should write right. So the energy absorbed or emitted. Yes, Mayam, you got disconnected.
Yes, sir.
Yeah, how? Which part did you note it down? So did you write all these portions? Did you write all these things? Where were you? Yeah, yeah. Tell me which part you have noted it down. Then and yes.
Sir, I was in E5 is equal to minus 13.6 by 20.
Yeah. So then you just take the screenshot of this part, right? Let me zoom this thing in, and you just take this screenshot and then you please start noting down from right.
Yes, sir. I took the screenshot.
Okay, then please note down because everybody is noting down. Okay, you guys quickly note it down. Then we'll do one problem, and then I'll start. Yeah, the spectrum, which is very important. So line spectrum, which would be emission or absorption. Yeah, whenever you guys have completed, please tell me, and then we'll talk about very, very important. This question is very important. So talk about that, and then we'll want to the next.
Yes, sir, done.
Then everyone, all of you guys, noted.
Yes.
Okay, what about you, Maria? Noted.
Sir, in the third point.
Oh, in the third one. Yes, guys, please wait a moment. Whenever Maria, yeah, that's noted it down, then we'll that question.
Done.
Then okay, so now let us do this question, and this is very important, right? This one is very important. So you will be given some energy level diagrams, right? And then they will ask you that which one is the correct one. So let's say you are given the energy level diagram. So this is minus 0.85 electron volt. This is, let's say, minus 1.5 electron volt. Then we have this minus 3.4 electron volt, and then the last one, so this was 1.5, and the last one is minus 13.6 electron. And one case is that
Yes, sir. Excuse me, sir. Can you explain this question again? My brother was going
yeah,
to India, so I was just saying goodbye to him.
okay, so welcome to India, right? Okay, yeah. So I'm just writing the question, and then I will explain this question.
Oh, okay, sir.
Right, and then this one is this one is right. So the question is that energy level diagram of an element is shown in the figure, right? Which transition? Which transition correspond emission of spectral line of wavelength 10.7 nanometers, right? So we have these are what? So these are higher energy levels. So this was n equals to 1. This was n equals to, this was n equals to 3. This was n equals to 4. So we have this A transition in which the electron is going down, right? It is going down from fourth energy level to the third energy level. So when we go down the energy level, so it emits the energy, right? So these are all emission spectra. These are not absorption spectra. So this A transition is from fourth to third one. This B transition is from fourth to second one, and this one is yeah. So this one is from 3 to second one. Then this one is D1 is from 3 to 1. These are all transition, and this transition is giving some wavelength, right? So this is giving some spectral line which corresponds to this wavelength, right? So we know that the energy difference between the energy level, that is how much? That is how much, guys? That is h nu. So this much amount of frequency it will emit. The energy that it will emit will have this frequency, right?
Yes, sir.
And now in here they have given the wavelength. So how do we relate the wavelength with frequency? So that is c by lambda, right? So then we can calculate that what would be the energy difference. What would be the energy difference when you have this wavelength? So let us calculate that first, right? So let us calculate this thing. So H is 6.626 into 10 to the power minus 34. C is 3 into 10 to the power 8 meter per second. And lambda they have given 10.7. And nanometer is how much? So this is 10 to the power minus 9. So this energy would be in joules, right? So how much is this thing? Okay, let me just calculate this. 6.626 into 3 divided by 10.7. This is 0.1935 into 10 to the power minus 34. And this is how much? So 10 to the power minus 26. And then this minus goes in the upstairs. So this is plus 9. This is how much? 0.1935 into 10 to the power how much? Minus. And this is 17. Right, guys?
Yes,
Right?
sir.
So this is in joules. But we can convert this energy because all the energies are given in electron volt. So we have to change this joule into electron volt. So how can we do that? We know that 1 electron volt is 1.6 into 10 to the power minus 19 joules. So 1 joule would be 1 divided by this thing. So 0.1935 into 10 to the power minus 7 divided by 1.6 into 10 to the power minus 19. This would be electron volts. So how much would be that? Let us divide this. Divided by 1.6. This is 0.109, right? And into 10 to the power minus 7. And this goes upstairs, so that would be minus 7 plus 19 electron. This would be 0.1209 into 10 to the power 2 electron volts. So this is 12.09 electron. So this should be the energy difference. Right, guys? This should be the energy difference. And
Yes,
in
sir.
which transition we can get 12.09. So we can get 13.6 and yeah. So let's say 4 and 3. So 4 and 3, this is 1 and 0. So we cannot get 12. Right? Right, guys?
Yes, sir.
And from B transition. So B transition is from this to this. So the difference would be roughly 3 electron volts. So this is not also possible. Right? From 3 to 2. So the difference is again 2, nearly 2. So this is also not possible. So what is the difference between this D transition? So difference in minus 13.6. So what is delta E in here? Delta E in here is minus 1.51 plus 13.6, and this we have already calculated. This was 12.09 electron. So this would be equal to Hc by lambda, which we have calculated 12.09 electron. So this would be the answer. This is the correct answer. So the answer would be, now this delta A corresponds to minus what would be minus 1.51, minus 1.51 to minus 13.6, which corresponds to minus 12.09. So the transition would be from how much? From n equal to 3 to 1. So 3 to 1, which is D transition. Is this thing clear? Is this question clear, guys? Whenever this kind of question comes, you guys have to calculate the corresponding energy difference and then check in your energy level diagram which difference is corresponding to that energy. Right? Only that energy would be permissible. Right? So is this clear, everyone? Is it clear?
Yes, sir.
Okay, please note down this question. So, yeah, this has been asked many a times. This one is a very important question. So they will give you these energy diagrams, and they will give you some absorption spectra. Yeah, in one case they will give you some absorption spectra. In that case only, yeah, in that case also you have to calculate this energy corresponding to this wavelength or frequency.